passwords stay safe while traveling across the internet? A network used by billions of people, including hackers actively trying to steal that information. The answer lies in a piece of technology working silently in the background every single time you go online: encryption. And more specifically, two different approaches to encryption that power almost everything we do digitally: symmetric and asymmetric encryption. By the end of this video, you'll understand exactly how both work, why we need both, and how they team up to protect you every time you open a banking app, send a WhatsApp message, or shop online. Let's start with the basics. What is encryption, really? At its core, encryption is the process of taking readable information, called plaintext, and scrambling it into unreadable gibberish, called ciphertext. This scrambling isn't random chaos. It follows a mathematical formula, and it can only be reversed by someone who holds the correct key. Without that key, the scrambled data is essentially useless. Even if a hacker intercepts it, all they see is meaningless noise. Now, there are two major ways to do this scrambling and unscrambling, and that's where symmetric and asymmetric encryption come in. Symmetric encryption. One key rules them all. Let's start with symmetric encryption, because it's the older and simpler of the two concepts. In symmetric encryption, there is only one key. That same key is used to both lock, or encrypt, the data, and unlock, or decrypt, it. Think of it like a physical house key. If you lock your front door with a key, the only way to open that same door is with an identical copy of that exact key. Here's a simple example. Imagine you want to send a secret message to a friend. You use a key. Let's say it's a specific code, like shifting every letter of the alphabet by 3 positions, to scramble your message. Your friend, who also knows that exact shift code, can easily reverse it and read your original message. That shared secret code is the symmetric key. In real-world computing, these keys aren't simple alphabet shifts. They're complex strings of bits, and the most widely used symmetric encryption standard today is called AES, or the Advanced Encryption Standard. AES is trusted by governments, banks, and tech companies worldwide because it's incredibly fast and secure when implemented correctly. So what are the advantages of symmetric encryption? First, speed. Because the math involved is relatively simple for computers to process, symmetric encryption can handle huge amounts of data very quickly. This is why it's used to encrypt entire files, hard drives, and databases. But symmetric encryption has one major weakness: the key exchange problem. Since both parties need the exact same key, that key has to be shared somehow before secure communication can begin. And here's the issue. How do you securely send that key in the first place, especially over the internet, without someone intercepting it along the way? If a hacker steals that one key during transmission, they can decrypt everything, past, present, and future, that was protected with it. This is a serious vulnerability, especially when you're communicating with someone for the very first time and have no secure channel yet established. This is exactly the problem that asymmetric encryption was designed to solve. Asymmetric encryption. Two keys. One solution. Asymmetric encryption, also known as public key cryptography, uses two mathematically linked keys instead of one, a public key and a private key. Here's how it works. The public key can be shared with absolutely anyone, openly, without any risk. In fact, you're meant to share it widely. The private key, on the other hand, must always remain secret and is never shared with anyone. Here's the clever part. Whatever the public key encrypts, only the matching private key can decrypt. So if I want you to send me a secure message, I give you my public key. You use it to encrypt your message. Once encrypted, even I can't reverse it with the public key, only my private key can unlock it. This solves the key exchange problem entirely. There's no need to secretly share a key beforehand, because the public key was never a secret to begin with. The most well-known asymmetric encryption algorithm is RSA, named after its creators Rivest, Shamir, and Adelman. RSA relies on the mathematical difficulty of factoring extremely large prime numbers. A problem that's computationally easy in one direction but nearly impossible to reverse without the private key. even with today's most powerful computers. Asymmetric encryption also enables something else incredibly important: digital signatures. By encrypting data with your private key, anyone with your public key can verify that the message genuinely came from you, because only you possess that private key. This is how software updates, emails, and digital documents are verified as authentic and untampered. So if asymmetric encryption solves the key sharing problem and offers authentication, why don't we just use it for everything? Because it's slow. The complex mathematics behind public and private key pairs require significantly more computational power than symmetric encryption. Encrypting large files or streaming data using asymmetric encryption alone would be painfully inefficient. The real-world solution: combining both. This is where the magic happens. Modern systems don't choose one over the other. They combine both symmetric and asymmetric encryption to get the best of both worlds. Here's how it typically works, using HTTPS, the secure connection protecting most websites you visit, as an example. When you visit a secure website, your browser and the website's server perform something called a handshake. During this handshake, asymmetric encryption is used briefly to safely exchange a temporary symmetric key, without any risk of interception. Once that symmetric key is securely shared, the browser and server switch entirely to symmetric encryption for the rest of the session. This is because symmetric encryption is fast enough to handle the ongoing flow of data, like loading pages, submitting forms, and streaming video, without slowing everything down. So essentially, asymmetric encryption solves the trust and key sharing problem, and symmetric encryption handles the heavy lifting afterward. This exact hybrid approach protects your online banking sessions, your emails, your messaging apps like WhatsApp and Signal, and virtually every secure connection you make on the internet. Why this matters to you? Understanding this isn't just theoretical knowledge, it directly impacts your digital safety. When you see that small padlock icon next to a website address, that's this entire process working behind the scenes to protect your passwords, credit card numbers, and personal messages from cyber criminals. Weak or outdated encryption, or systems that fail to implement these methods correctly, are exactly what hackers exploit to steal sensitive data. This is why cybersecurity professionals emphasize using updated software, secure connections, and reputable, well-audited applications. Wrapping up. Let's recap quickly. Symmetric encryption uses a single shared key. It's fast but has a key sharing problem. Asymmetric encryption uses a public and private key pair. It solves the key sharing problem and enables authentication, but it's slower. And in the real world, we combine both: asymmetric encryption to safely exchange a key, and symmetric encryption to handle the actual data efficiently. Together, these two methods form the backbone of nearly every secure digital interaction you have, from banking to messaging to browsing. If you found this breakdown helpful, follow the page for more deep dives into cybersecurity concepts explained simply, and stay tuned, because next we'll be covering how digital signatures and certificates actually verify that the websites you trust are really who they claim to be. Stay safe out there.